Okay, so boom. You're walking along and you're vibing. As in, literally, you're vibing. You are constantly creating vibrations. With every step and every beat of your heart, you're releasing potentially useful energy. You remember 1983's ridiculously terrible Superman 3 when Richard Pryor's character rerouted all the fractions of a cent to his account and ended up with buku bucks? That's essentially the concept of energy scavenging or energy harvesting. With energy scavenging, we implement devices that can collect bits of wasted energy from a given process, whether that's in the form of movements of the human body, foot strikes on pavement, the vibration of railways as train cars pass over, or even ambient radio waves. The second law of thermodynamics tells us there's always some amount of waste energy left over. In this analysis, we discuss how piezoelectric energy harvesters can conserve some of this energy. These devices are also subject to the laws of thermal efficiency, but nonetheless, a well-placed piezoelectric walkway or roadway can turn pavement producing no energy whatsoever into a source worth many kilowatts a day. So first, what is piezoelectricity? A piezoelectric material is one that produces a current and voltage when placed under mechanical stress. Naturally occurring quartz and tourmaline have this property, in addition to man-made ceramics such as lead zirconate titanate or PZT. A device using piezoelectric material generates power by repeatedly stressing and alleviating the material, that is, compressing and decompressing or vibrating it. Piezoelectric harvesters are considered regenerative power sources in that they produce energy as long as the material is under the cycle of strain, making them an ideal candidate for devices needing long-term energy at low maintenance, such as a pacemaker for the heart or a sensor in a remote location. This is an emerging technology, with the main barrier being the cost of materials and designing for long-term use and efficiency. As a renewable source in roadways or walkways, piezoelectric energy is still quite cost prohibitive. For example, piezoelectric tile from Sustainable Energy Floor is approximately $1,000 per square meter of tile, with an average energy density of only 28 watts per meter squared, compared to the 1,368 watts per meter squared for direct solar power. Outside of manufacturing, it does boast zero emissions compared to the 26.2 kilograms of CO2 that would be released from burning an amount of coal equivalent to the production of 1,000 square meters of piezoelectric tile. Unfortunately, the least amount of data is available on the most promising application of this energy technology, biomedical implants. For devices requiring only microwatts of energy, this technology solves the issue of battery life while also being efficient. Only centimeters of piezoelectric material are required to power a pacemaker or internal stimulation device, and the main barriers for biomedical implementation are related entirely to engineering devices that will last long-term and are biocompatible. Piezoelectricity could reduce our dependence on electrochemical batteries for these purposes and introduce regenerative power for many applications, revolutionizing health monitoring and saving lives, in addition to enhancing data collection in remote locations, such as ocean buoy sensors powered by fluid movement or seismic monitors powered by vibration.